All right, for our lesson today, we're going to talk about a couple different things. I want to start with this idea of voltage drop. So with voltage drop, the idea is that you are going to see that your battery is going to give a potential, a boost to the electrons. It's going to cause the electrons to start flowing. And it won't let me do the pointer right on the video, but so I'm right above it. You can see here that if you go from the left to the right of my light bulb, there's a potential drop. The greater the potential drop, the brighter your light bulb will be. So we can see just a basic example of what it looks like as the electrons go around in the circuit. And I want to compare that to what we're going to see if we have no battery. No light bulb. So in this case, in this video, I made a circuit that was just wires and batteries. So the electrons are getting a boost, and there is something called resistance in the wires. So you do see these numbers that go around. They do get smaller and smaller as they go around your circuit. But this is an example of something you do not want to do with a battery. If you look at the battery on the left, as I complete the circuit, it's going to start flashing red, and those electrons are going to go through very, very fast. This is called short circuiting. That's a short circuit to the wire. And if we were in the classroom, I would show you some wires that Hendrix has in his room that he's done it before and I've done it before. That when we've been demoing light bulbs in the classroom, we actually have managed to melt the wires together because something short-circuited in the circuit we were dealing with and caused it to overheat to a point that the plastic around it melted. All right, so here on the side I've got 3 different configurations now, and it is a little bit small. I apologize for that. But what I wanted to show you is what the voltage drop looks like when I keep adding light bulbs. So in this example here, I just have the one light bulb, and I've highlighted in gold around it how big the circle is how physics classroom is denoting how bright the glow is. And when I multiply my number of bulbs by 3, look at how much smaller these circles get. In other words, they're much, much dimmer than my circuit of 1 light bulb was. And then here I've added 9 light bulbs to my circuit, and they get so much smaller still. So you're not getting much light out of that, and maybe not even any noticeable light when that many light bulbs are in series. When we have them in a circle like this, our wires look like they're creating a circle. That's called in series. Alright, so here I have some videos where I created the demo that I would have, and it's a little bit hard to see certainly in the light, but I hope you can see a little bit how the light bulbs brighten as I connect the wires to the batteries. And I'll upload this presentation itself on Canvas so you can play with those videos and see what you can see. Alright, so what's happening here is when you experience a voltage drop, your light bulb will light up. And the electrons they're given a boost as it goes through the battery. That's how the electrons start flowing. But every time it crosses a light bulb, there is a voltage drop. And as you use it up, you can't gain more without having another power source. So if you have just one light bulb, then that light bulb has the drop of the entire gain of the battery. So if it's a 9-volt battery, you'll have a 9-volt drop. But if you start adding light bulbs into your circuit, then you have to divide that potential drop, that total drop, among how many items you have in series. Which is why, like I said, the bigger the voltage drop, the brighter the light bulb. When you have all these smaller voltage drops, you're going to get a much dimmer view. And I will upload too some videos to your Canvas where I did the experiment here with your light bulbs, but I did them in the dark so you can see them a little bit better. All right, so, oh, where are we at? Went too far. Hold on, there we go. Okay, so you can connect your wire in a couple different ways. So all the examples I showed you are series circuits, and like I said, that's when everything looks like it's making a circle. Parallel is another way that you can put together your wires. And it turns out that when you put your wires together in parallel, something completely different happens. So here I've got some videos of me connecting connecting light bulbs in parallel. I'm not sure why they're not playing. But one thing I do want you to notice here on the still frame is the brightness of each of the light bulbs is actually fairly similar. When you're connected in parallel, we don't have the voltage drop that we would have when we were in series. I'm not going to talk about that in detail right now, but I do want you to be looking at it and thinking about it, and I will bring that up in one of the next lessons. Alright, so the next topic of the day, we're going to start talking about resistance. Now, if you've had either Hendricks in class or Webster, I do expect that you probably have talked about resistance. Resistance is just the hindrance to the flow of charge. Your electrons, as they go through the wire, there are different reasons why they will get slowed down. So think about your wires like pipes. If you have a nice clear pipe and you're running water through it, the amount of water that can go through the pipe will depend on how long the pipe is, how wide the pipe is, and if there are any obstructions in the pipe. So for comparison's sake, I have some pipes up here that have obstructions, which of course the water won't flow through as easily. Now, none of these are sewage, at least the internet said they weren't. This picture and this picture are pictures of sprinkler systems in buildings that were not maintained, and there was corrosion in the pipes that built up, and because of gravity then it fell towards the bottom and it filled the pipes. And then this picture is of some roots from a plant that cracked through the pipe and then they grew through the pipe. It's actually a pretty common problem to have with the pipes that run into but mostly out of your house, depending on what they're made out of. Alright, so in a wire, your resistance is affected by basically the same things. The length of the wire will affect the resistance. The longer the wire, the more resistance it will have, just because as it goes through the wires, there are more atoms for your electrons to collide with. How wide the wire is also a consideration for resistance. The more narrow the wire, the less resistance you'll have. The more narrow the wire... Hold on. Yeah, the more narrow the wire, the more resistance you'll have. Just less electrons can flow through. And the wider the wire, the less resistance you'll have, because more electrons can flow through that cross-sectional area. And then the next consideration is going to be what material are your wires made out of. The better the conduction of the material, the better the resistance, or the lower the resistance. So some common materials that we have here, I pulled this just right from physicsclassroom.com. Silver, we see here, is one of the most conductive materials on our list, and therefore has one of the smallest resistivities. Copper and gold and aluminum, also very, very low resistance in those materials. And as we start to get down towards our insulators, you see that their resistivity grows tremendously. These are things that the electrons are going to have a really hard time to move through these items. And if you're trying to force it enough, then they will heat up more than we'll have in other places. High resistance can cause high heat, like I said earlier. Alright, so the unit of resistance here is called the ohm. This is the Greek letter, omega. And the ohm, of course, was named after a scientist who did research in this area. In this case, named after George Ohm, born shortly after the American Revolution. And this symbol here, these squiggly lines that kind of remind you of a heart rate monitor, this is the symbol that we'll use for resistors in a circuit diagram. So here's an example of a circuit diagram, and you can see all of these resistors in the diagram. Don't know what this is for exactly. Something with a camera. I don't know. My guess is probably for the light bulb that goes with the camera. I didn't look that up. I just copied the circuit diagram. But another thing to make note of, is when you have your power source. Your power source is denoted by these solid lines, these parallel lines, and the side that has the longest line is always your positive side of your battery. The side that has the shortest side is always the negative side of your battery. Alright, now Ohm, his biggest claim to fame is Ohm's law. Ohm's law is an equation that we will be using for the rest of the time we do circuits. And there are 3 different ways you can write the equation. I personally usually will use this one. It doesn't really matter which one you use. They're all the exact same equation, just solved for a different letter in each case. But V equals IR is just my favorite. Now V is, it's your voltage, your measure of your potential drop, your potential, I always want to say energy, but it's actually not an energy. We'll talk more about that later. But just your potential drop. And the unit for voltage is the volt. It's probably one of the most convenient units that we have, because it really is pretty much the only time I can think of where the unit matches so closely with what the quantity is. Just like for when we're measuring distance, we measured it in meters. We didn't have a unit called distance. Alright, so next we have our I, represents current. I will admit to you, I'm not sure why we use the letter I. I can see mathematically why we wouldn't want to use a C. We use C for other things. C can look too much like a parentheses. But for whatever reason, we do use the I. And the unit for current is the ampere. And your current is just your measure of how many electrons are flowing through a wire at a specific point while the circuit is hooked up. Okay, so solving problems. Let's finish on a problem. Here I've got an example problem. Now this is technically 2 problems. I just solved this one. So we have our battery, our resistor, and we have an ammeter measuring our current. We want to know how much resistance this resistor has. So we pull out our equation. We identify our variables. We plug in our numbers and we get 12 equals 2R. Solve it for R and we get the resistance of that resistor must be 6 ohms. Now I'm going to leave it to you to do this one. This is a problem that does come directly from your homework. So you can check your homework. It'll be on Canvas, and I'll post some more videos for you with you to see on that assignment. And we'll keep talking about this on Friday and next week. enjoy, and I will talk to you all on Thursday when we have our conference.